Welcome back, everyone, to the eCoreAcademy e-learning platform. My name is AJay Raj, back with yet another Algebra 1 video for you all. And today's lesson topic is precisely on piecewise-defined functions. Now, today's topic, we're going to be getting into what exactly piecewise-defined functions are and exactly how you graph them. So looking at situations in which we take a situation where we need to develop an actual figure, and I'll show you how to actually develop piecewise functions by utilizing existing basic functions. Also, we'll be able to identify by looking at a graph what are the various different piecewise functions or subsections of the graph that make up such a complex graph. But without further ado, I'm going to be explaining that throughout the lesson, so do not be alarmed or worried at all if you don't understand what they are. It is a rather confusing term, piecewise-defined function, but it is a very necessary term in describing them. These are all things that you know, but just the process itself is something that will be new to you, and you'll carry on all throughout your academic mathematics careers. So before we jump into today's lesson, please make sure to do 4 things. Please make sure to smash that subscribe button, hit that like button on this video, turn on post notifications, and feel free to hit that like button also just with that YouTube algorithm, as well as commenting down below along with liking. Those are 2 things that really help our YouTube algorithm out, helping us get more recognized so we can reach more people and help more people out along with these topics. So without further ado, once you've done all 4 of those things, let's jump right into it. So let's take a look at a basic overview of what exactly piecewise-defined functions are. I'm sure many of you haven't actually heard about it coming into Algebra 1, but now that you're hearing it, you might think it's a very complex topic, something that involves a lot of new arithmetic concepts. Well, it really isn't. You're just combining all of your previous knowledge of inequalities and your basic knowledge of basic graphs that we've already covered throughout Algebra 1, and we'll just be adding to that, combining those properties of inequalities and graphs together to make our piecewise-defined functions. All right, so let's look at the basic definition and the basic purpose of having a piecewise-defined function. So a piecewise-defined function, by its mathematical definition, is a function that is inclusive of segments of various different functions to create one fluid function. The traditional piecewise function would not have any breaks. However, you can have a piecewise graph that does have, not necessarily fluid, but has different sections and different subsections of previously existing functions. So essentially what you're doing is you're taking your general functions like your linear equations, your parabolas, and then basic shapes like your circles and other figures that can be created by single function equations. When you take those and you alter them, essentially what you're doing is you're cutting out sections of those given functions. When you're creating a function with a graph, you're creating the general shape. With piecewise-defined functions, you're essentially taking a section of that given graph that you're graphing by utilizing certain constraints with inequalities to actually get those different sections of your functions and then attaching them. So essentially, you're just piecing together different subsections of your original graphs by defining them with inequalities. They're given a range of where exactly they should be in terms of coordinates, and then you're attaching them together to create entirely new figures and graphs, maybe even replicating real-life objects, which I'll show you a bit of artistry at the end, how you can really practice with these constraints. So these functions are created, like I said, by putting constraints on either of the axes, either your x or y axis. Remember, once you limit your axis to a certain constraint, it cuts out the entirety of that fluid line. Most of the graphs that we create, like lines and parabolas, they go on forever. When you add a segment or a constraint of it, you're getting that segment that is finite. So you know a given end and a given start point, and you'll see that section of the graph created. But of course, with more practice, we'll see what that looks like visually. And lastly, this is an easier way to identify complex graphs with easier subsections of a function. So when it comes to larger graphs that are much more complicated, that you cannot exactly identify by one single equation, it might be a very weird graph like a frequency chart. You can't necessarily identify it by a single equation, but you can break it apart into different linear equations, essentially attaching different linear equations together to get that overall essence, how to define that graph. So you're essentially taking a complex figure, breaking it apart into subsections, and defining those similar basic sections separate. And putting restraints on the axes involves and compound inequalities. If you recall our and compound inequalities, you take your variable and then you put it in terms of two other constraints. It's essentially comparing a number and where exactly it lies in between. Say, for example, 2 is less than x is less than or equal to 3. That means x will be within 2 and 3. So that's your basic and compound inequality. We'll use that built-up knowledge to actually graph this, to use this in graphing practice. So graphing piecewise-defined functions. Let's exactly look at what the process is like, and then of course I'll show you an example, and then we're going into more complex artistry with this whole piecewise-defined function graphing. So what exactly is the process? So number one, you would identify all of the original functions of the graph that you would need to graph. So say, for example, the basic functions, the basic, like your lines, your parabolas, your circles. What are the basic shapes that you need in the graph? The original functions. Then secondly, you would determine what portions of the graph are going to be represented. So say, for example, if you're taking your line, say, for example, you're trying to create a certain shape or represent a certain frequency chart, you wouldn't exactly have a line because a line goes on infinitely, it cannot be measured relatively. So what we would do is we would merely take a subsection of that line we'd merely be taking a subsection of that line, so now we have to determine what that constraint is. Or, like I said, a little bit more complex, if you take a circle and you create the graph of the circle, you graph the circle, and you realize that you only need half of a circle, a semicircle, then of course you would determine a semicircle and then put constraints thereof. And lastly, number three, you'd plug in your constraints, essentially your inequalities for your graphs for each separate function, and then essentially that would cause a break in that whole entire figure, like a circle. You put a constraint on it to only go from the center to the exterior point. You'd get a semicircle, and by doing so, you would get your essentially you'd graph your subsections and get your piecewise-defined functions. So, just as an example, you take that semicircle from your original circle. So you take that original circle, create the graph of it, x minus h squared plus y minus k squared equals r squared. You take that original graph, and then essentially you add a constraint to it to make it a semicircle. And we'll get into that in the last slide, especially with complex figures. All right, now let me show you some common figures that you're going to come across when it comes to splitting up or looking at subsections up. So what are some common subsections? So let's take a look at our original linear graph, a line. This is one of the common graphs defined by the equation of y equals mx plus b. A common subsection of a line would be a line segment or a linear array. Now, how would that look? So remember, whenever you're taking a subsection of a line, we know that a line goes on for an infinite amount of time. It goes on infinitely, so we can't give it a relativity. So when it comes to creating a subsection, you cut out a chunk of that line, and that would be known as a line segment. Because when you're creating an and inequality, you're always going to have a finite end and a finite beginning. So therefore, you're going to create a line segment or array. Then for your parabolas, as shown, you could create a halved parabola. So you can use a parabola and start to cut out chunks of the parabola to create different curves that you might need to represent in your graph. So say, for example, you might have the parabola, take only half of the parabola that kind of looks like an exponential equation. You're essentially splitting it down the center where the vertex is, essentially cutting out everything else from the right, giving a constraint only to allow from everything from the center to the left. And then finally, like I showed you before, you can have a circle, and you can translate that into a semicircle with constraints, some common subsections here. These are all original graphs that have common function equations. And then over on the right, you have your abnormalities, those essentially altered forms of your original equations. All right, now let's get into our example, showing you exactly how we're going to be utilizing those processes, our basic knowledge of what these subsections are supposed to look like, and we'll use this in our example of this frequency graph. All right, so we're going to identify the original function of the original functions of this piecewise function and determine what their constraints were. So let's give our example. We're going to be given the actual piecewise defined function, determine the original function, and also the constraint. So here's the graph of the function. So as you can see here, it's essentially 3 line segments attached together. This is something often found in a frequency chart, also like a performance chart, just some sort of documentation chart. So as you can see, it's 3 different sections indicated by 3 different colors. They're line segments, but we know that line segments are subsections of lines. So therefore, we can start to use our knowledge of y equals mx plus b equations and create our original equations. So the yellow line over here is going to be y equals x. You can see that it intersects 0, 0, and it has a closer slope to 1. So we're going to estimate it at y equals x. Then, of course, the original equation for the red line segment is going to be y equals negative 1/2 x plus 4. If you extend it onwards, you can see it approximately intercepts the y-axis at 4, and it's about a much slower slope, so it's going to be 1/2, and it's negative because it's going in the opposite direction. And then, of course, with your green graph, your green line segment, it's going to be y equals x minus 3. As you can see, it has the same exact steepness as our original yellow line. However, it is shifted to the right a lot more, and its y-intercept is at negative 3. Now comes the trickier part. We're going to actually find the constraints. So if we take our original equation of y equals x, we have to identify what portion of y equals x is shown as the yellow colored line segment. So in order to do so, let's put it in terms of our x-axis. So what exactly are the constraints on the x-axis? So what exact x-coordinate pairs are actually being used in the line segment? Well, every single x-coordinate from 0 to 5 are actually representing the line segment on that given line. So all x values from 0 to 5 are actually being used on the line segment. Therefore, your constraint would be 0 is less than or equal to x is less than 5. The reason why we leave less than 5 is because the red line is connected to the yellow line, so we don't want them to necessarily overlap. We only want one to connect to the other. So once we do that, we've identified all values from 0 to 5 on the x-axis are going to be valid for your yellow line. All right, now for our green line, for our red line, or for our green line, we'll do our green line now. We know that our constraint is going to go from 8 on the x-axis to 14 on the x-axis. So 8 is less than or equal to x is less than or equal to 14. Shows that little snippet of your entire line linear function for x minus 3. It goes from 8 to 14, all x coordinates included for that line segment. And finally, for our red line, we have 5 is less than or equal to x is less than 8. It's between your 5 and your 8, the starting point for the green line and the ending point for your yellow line. Every x value from 5 to 8 is included in that line segment from the original function. So as you can see here, these are merely snippets. When you take certain parts of your function, you give a certain range either for your domain or your function, you give that range of values, and you're given a subsection of your original function. All right, now let's go to a Desmos activity. So what we're going to do here is, for the last part of this video, we'll go through some basic graphing problems on a graphing calculator, one of my favorite websites. It's at desmos.com. And this website provides Desmos graphing calculators. So we're going to go to the Desmos graphing calculator, and I'll show you what these constraints look like and how to input them, what are the notations to input, and how you can utilize them to ease up your life, when trying to calculate more complex piecewise-defined functions. So the shape that we're actually going to try and create on this graph, we're going to keep this goal in mind. We're going to try and create a simple square with a semicircle inside. This is a great way if you use any shapes or any figures or letters that you want to create on a graph itself. It's a great way to practice with piecewise-defined functions. All right, so let's try and recreate the original figure that we had. The original figure that we had, of course, was a square, and then inside we had a semicircle touching the exterior side of it, aligned up with the very center of the square. So let's try and recreate that. Let's start off by graphing out, a simple line. So let's start off with the line y equals 4. All right, that's our basic line. Let's keep that as our starting top part of the very square. Now let's create another line, and this line is essentially going to be the left-hand side. It's going to be your left-hand side on the screen. It's going to be left-hand side of the square. So let's create that. In order to create that, it's going to be the line of x equals 2. That's going to intercept our top line, and as you can see, we've already created half of our box. Now let's go for the third line. We're going to create the very bottom line here, and in order to create that, it's going to be an equal distance from the center of the box. So from 2 being the center of the box, we're going to go down 2 all the way to 0. So that means y is going to equal 0. And then finally, our last part of the box is going to be the right-hand side of the box, and that's going to be x equals 6. So once we have this in place, as you can see, we've kind of already etched out our box, the basic, structure of it. And now the last thing that we need to do here in terms of graphing our original equations is we have to graph our circle. Remember, in order to create that semicircle, you have to have an original graph, so we're going to graph our circle. We know that the equation of a circle is x minus h squared plus y minus k squared equals r squared. So your x coordinate minus your h plus your y coordinate minus your k equals your radius squared. So we know that our center of our circle is going to be at the center of the box. The center of the box, as you can see, is going to be 4, 2. Therefore, we can start plugging that into our equation. So we have x minus 4 being our x coordinate. And then, of course, we're going to square this value. Then we're going to add it to y minus your k value being 2, your y coordinate. And then you're also going to square that. And finally, this is going to be equal to our radius squared. We know that the radius squared is going to be the distance from the center of the box to the outside, or the center of the circle to the outside. That's going to be a distance of 2 from the center of 4, 2. So since it's a distance of 2, we're going to square that, and we get 4. So that means this whole equation is equivalent to 4. And as you can see here, our circle has been created, centered, touching all points, all sides of your square. Now, the last thing that we need to do is we need to go back and input all of our constraints, and then of course we'll get the desired objects. So first thing we're going to do is go and look at the lines, the edges of your boxes. We're going to try and eliminate all the excess part of the line that we don't want, and only keep the line segments that we do need to create the box. So for y equals 4, the constraints that we actually need to put on this this side of the box is going to be so that it's between 2 and actually 6 in this case. So in terms of y equals 4 being our red line here, it has to go from 2 to 4 in order to align with our circle here. So what we're going to do is we're going to put our constraint, we're going to put an open brace or a soft bracket, we're going to put 2, and then of course we're going to put it in terms of our x-axis in this case. So we'll say that it's less than or equal to x is less than or equal to 6. And so as you can see, that line segment is just formed between 2 and 6 on the x-axis. Now, when it comes to x equals 2, since this is an x equals value and it has to do with a vertical line, we know that we cannot put a constraint with an x on the x-axis. It's going to eliminate the whole line. So instead, we're going to put this in terms of our y, our y coordinate. Any other line or any other part of the graph you can put in terms of your x. I like to keep it consistent with my x. It doesn't really matter, but only in the circumstances must you use y. All right, so in this case, we'll open up our bracket. We know that the starting point of this equation, of this box, is going to be from 0, and it's going to go up till 4 on the y coordinate. So we're going to make it 0 is less than or equal to y is less than or equal to 4. So we know that all y values from 0 to 4 on this line are going to be applicable. So it creates that line segment that's 4 units long. And then let's close it off. And then for y equals 0, we know that it has to be between 2 and 6 to get that 4 units on the very bottom. So we're going to put a constraint. 2 is going to be less than or equal to x is less than or equal to 6. And then, of course, we'll also close that off. All right. And lastly, for x equals 6, that's going to be our final vertical line on the right-hand side. We're going to create that soft bracket again. We put our soft bracket in that time. And then we also know that it's going to be between 0 and 4 as well to align with its opposite side. So 0 is less than or equal to x is less than or equal to 4. All right, so that'll be it for our sides of the box. And now finally we have to deal with our circle. We just have to create a semicircle leaning just to the left-hand side of the circle. So what we're going to do here is we're going to put a constraint here. We know that the circle, we know that 1/2 of the square is going to be from coordinate y.2 to the from the x coordinate 2 to the x coordinate 4. That's going to be a total distance of 2 because the side length of the entire box is 4. So we're merely going to split that in half. We have that 2 to 4 there. X has to be between 2 and 4 to create our semicircle on the left-hand side of the box. So what does that mean? We're going to open up another soft bracket here. We're going to say that 2 is less than or equal to our x value. We'll keep this in terms of x. 2 is less than or equal to x is less than or equal to our 4. So that it only occupies half of the given square. Finally, we'll close that entirely up. So now that we've completed the entirety of our graph, successfully here, just put that in terms of y, I apologize. So once we've created the entirety of our graph here, of course, with our our x equals 6 and our x equals 2, we had to use our y values there. As you can see there, I just made a mistake, but you cannot use x values there. So when using x values, you can't use it for x values for a vertical line. You can only use it for horizontal and any other lines. I like to put it in terms of x, but these are special case scenarios when you have to put it in terms of your y. So just a common mistake out there. All right, everyone. So, that'll be it for today's video. But before we get to the outro, please make sure to go ahead and try this on your own. Even if you want to go out, I challenge you to probably even try and draw out your entire name on a graph using constraints with just basic linear functions. If you want to use circles, parabolas, knock yourself out, but just try and write out your name in the most complex way possible that you can. Maybe bubble letters, try and challenge yourself maybe with cursive, with a lot of curves. This really helps you practice constraints. Alright everyone, so that'll be it for today's video. I hope you guys enjoyed. This has been the eCoreAcademy e-learning platform, so please make sure to like and subscribe down below and turn on the post notifications and leave a comment down below. Please check out our website at www.ecoreacademy.org. We have lots of interesting content out there for you all to see. Some really new fascinating topics and just full unlocked course access to notes, quizzes, and worksheets to help you along with our videos. Please also email us at eCoreAcademy@gmail.com if you have questions, and check out all of our socials, Pinterest, Facebook, Twitter, Instagram, and TikTok. We also have some really fun and some non-academic content out there for you all to see. So I hope you guys enjoyed this video. This has been AJay Raj, and I'll see you guys in the next one. Peace.